Hi. So before we start, get your blue books out and get doing your retrieval roulette. So pause the video, answer these questions, and then I'll put up the answers so that you can mark them. Right, here's the answers then. So again, pause, mark and correct your work, and then get ready to start. Right, so we're starting at page 100 in our notes today. So if you get your folder open at page 100, then you'll be ready to go. Get obviously something to write with. Well, you have that already from doing your retrieval roulette. Okay, so just before we start on page 100, which you can see is getting the components of a vector, I just want to spend a wee minute or two reminding you what we were doing just before Christmas there. So just before Christmas, we were looking at how to find the resultant of two different vectors. Okay, so I'm going to talk here about forces, I suppose, more than anything else, but this does still apply to any other vector that we will be working with. So if I have an object here and I have a force of 10 newtons acting that way and a force of 7 newtons acting that way, then we can find the resultant of both of those two vectors. So there's two different ways that we can do that. We can draw scale drawings by adding them tip to tail, remember, and then measuring the distance from where we started to where we ended up, and that's going to be our resultant. So the resultant is just the combined effect of the two or more forces or any vector. So it can be it just has the same effect as having both of those. So you could replace these two with one resultant force. So remember, one way you can find the resultant is to do your scale drawing, but today's work is all about calculation, so I'm just going to recap the calculating way here. So if we were asked to find the resultant of both of these, we would draw them same as the other way, tip to tail. Doesn't matter what way round you add them. So there's my 7 to the tip of this. I'm going to add the tail of the other one, which was 10 newtons. And then our resultant is the one that takes us from where we started to where we ended up. And then to find that, we would just use Pythagoras. So r squared would be 10 squared plus 7 squared. And then if I solve that, I get 12.2. I've just gone to 3 significant figures, and because it's 4 newtons. Now, the other thing then that we were doing was applying trigonometry to this. So remember, vectors' direction matters, so that means they'll have an angle. So say we wanted that angle, call that theta. And we can just use our bog standard trigonometry here. So this would be our opposite, this would be our adjacent, and this would be our hypotenuse. So to find this angle, because we know the opposite and the adjacent, more than likely we would use tan. Could use any of the other ones, but because any of the other ones involve us using r, the resultant or the hypotenuse, then if we figured that out wrong in the previous part, it's going to be wrong in this part. So try and stick to the information they give you in the question. So tan theta is opposite over adjacent, which is 10 over 7. So then theta is going to be tan to the minus 1 of that, which gets 55.0. Okay, so what we're going to be doing today is like the opposite of that. So we are taking effectively, I like to think of it like this, we're taking the resultant and figuring out what the two perpendicular components that would combine to give you that resultant would be. So let's go to page 100 and page 100. So this skill here that we're looking at today comes up in a lot of our other topics. It's going to come up in moments, it's going to come up in projectiles. I can't think of any other, but it comes up in a lot of stuff for the rest of the year, so it is really important that we get this skill down. So often we have to split a vector up into two perpendicular components, and it'll always be perpendicular that you are splitting up into. Generally I'll go vertically and horizontally, but just like in maths, sometimes it could be parallel to a slope and perpendicular to a slope, as long as the two things are perpendicular to each other, and that will be called resolving. So whenever you resolve a vector, force in this case, you're going to get the components. So you will hear me using that phrase an awful lot, the component that acts this way or the component that acts that way. So our little example that we have here, we can resolve the vector f below into two components which together have the same effect as the original vector, and we just use simple trigonometry. So hopefully you can see that it is just the reverse of combining to get the resultant. Okay, so you're going to have to keep pausing this to write things in, right? So if we think of this vector f as the resultant of two vectors, then the vector diagram would be like this. So you'll have some component acting across here and some component acting up there, with f being the resultant. So get that written in for me. Now, if we were to mark those components onto this diagram, like again, we're doing like the opposite of drawing tip to tail. We're taking the tip to tail ones and drawing them coming from the same point. So we'll have this component, I've just called like the horizontal x. So fx is just the horizontal component of this, and then fy would be the vertical component. So this would be our original situation. Now I'm going to go through here like where the components come from, the trigonometry behind it. I just think it helps, and then it means you can apply it to whatever the situation is. In reality, you'll just get used to using this and you'll be able to do it automatically. Okay, so just underneath that, can you write with me here? So we can use simple trig to find the size of fx and fy. So I'm going to take this little diagram here. So we have our original force F. We know that's going to have some component there, Fx, and some component here, which was Fy, and this is theta. So if this is the angle that we're talking about here, then this is the opposite, this is the adjacent, and this is the hypotenuse. So let's look at the horizontal one here first of all. Because we're always going to be using our original vector here, which in this case is this, then that's going to be a feature in this. So if I was wanting to find this, the horizontal component, it would be the adjacent and the hypotenuse I would use. So that's going to be cos. So cos theta is adjacent over hypotenuse. Or for this exact one, it's going to be fx, because that is the adjacent, over f, which is the hypotenuse, which means if I multiply up by f, I get that the horizontal component is going to be our original force F cos theta. Okay, and I'm just going to do the same for the horizontal one. So for this horizontal one, or the vertical one, sorry. So this vertical one, which is Fy, because it's the opposite, our original one is the hypotenuse, opposite and hypotenuse, it's going to be sine. So sine theta is O over H, which is Fy over F, and again, multiply up, we get Fy equals F sine theta. Now, be super careful. It won't always be the case that horizontal is cos and vertical is theta. It all depends on what angle that they give you. So I'm sure you will remember this if you've done this in maths, but the little sneaky way that you can remember to see if you happen to do these every single time is if to get to the component you're looking for from your original one, you go across the angle, then it's always going to be cos. If you don't, then it's sine. So make a wee note here, cos, oh, not even on, across. Okay, so cos across is the wee rule that I would always use to remember, and all it means that if this is my original vector and I want to find the component that I go across the angle to get to, then it's going to be cos theta. And if it's not, if it is like, if I go back to my original one here, I don't go across the angle to get to that, then it's going to be sine. So I'm actually going to summarize that down at the bottom here. So here's my original F, which is at some angle theta here. It's going to have a horizontal component Fx, and a vertical component Fy, which is F sine theta, and this one's F cos theta. So I'll go back over that cos across thing again. So to go from my original to the horizontal component, I go across the angle, so I take cos of it. To go from here to here, I don't go across the angle, so it's sine. Remember, this is just like taking one original vector and finding two perpendicular ones, which will have the exact same effect as that original one. And by doing this, it just means we'll be able to start to apply Newton's laws and things like that once we get there. Okay, over onto 101 then, we are going to do a few examples before you just get practicing this resolving technique. So example 1, a particle has a force of 50 newtons acting at an angle of 35 degrees to the horizontal. What are the horizontal and vertical components of the force? So here's my angle, or sorry, here's my force, it's 50 newtons at 35 degrees, and we have to find what the horizontal one is. I'm going to go H this time for horizontal, why not mix it up, and FV for vertical there. So applying our wee cos across rule, the horizontal, FH, well, to get from my original 50 force to the horizontal, I go across this angle, so it's going to be cos. So it's going to be 50 cos 35. So the original force cos the angle, and that gets 40.96. Okay, and then the vertical, to get from my original over to here, I don't go across the angle, so it's not cos, it's going to be sine. So it's going to be 50 sine 35, which gets 28.68. Okay, if you want to always use cos, say, then you could just figure out what this angle here would be, and then it would just do cos of it. So what is that going to be? 55. So cos 55 would give you the same answer, but that's a bit of a faff. Right, before we start example 2, please can you change the word mass to weight before I start twitching here? Don't know what came over me whenever I typed it. So a weight of 10 newtons is sitting on a plane inclined at 20 degrees to the horizontal. What are the components of the weight of the particle acting parallel to and perpendicular to the slope? So this is just to show you that it doesn't always have to be vertical and horizontal. As long as the two components are perpendicular, we're landed. So let's sketch our diagram first of all. So we have our slope, right? And then we've got this weight here. The slope is at 20 degrees. And this is asking about the weight. So for now, the only force I'm going to mark on this is the weight of the object. So the weight is always going to act vertically down the way. Okay. Now, the question has asked about the components parallel to the slope. So this weight is going to have a component here, and I will call it F par, and a perpendicular component, which I'll call F perp. Okay. Now, this angle 20 here is always going to be, well, whatever this angle is always going to be this angle as well. If we think through the maths of that, if you just think about a triangle, this is 20, because this is like the ground, this is horizontal, and this is acting vertically, this is a wee right angle. So we've got a triangle here, these all have to add up to give us 180, so this angle is going to be 70, and because this and this are perpendicular, then these two have to add up to give us 90. Right? You don't have to prove it every time, but I just wanted to show you where it came from. So this angle here is always going to be the same as this angle. Now, for part A, parallel. So the parallel component of this is going to be the weight, which I should have marked on was 10 newtons. And then because we go across the angle, it's going to be cos 20. Oh, I tell a lie, I was talking about the perpendicular one there. So let's actually do the parallel one. So the weight is the 10. We don't go across the angle, so it's sine. And then our angle is 20. So 10 sine 20 gets us 3.42 newtons. One way that I remember this as well is that sine for sliding down the slope, the one that's parallel to the slope, is always going to be sine of the angle of the slope. Right, part B, the perpendicular one. So it's going to be our original force, which is 10, because we do go across the angle, cos 20, and that gets us 9.40. Okay, make sure you get that all written in. Okay, 102 for example 3. So a water skier is pulled up a ramp by the tension in the tow rope. This is a force of 300 newtons acting horizontally. The ramp is angled at 20 degrees to the horizontal. What are the components of the force from the rope? Right, so let's get our diagram drawn first of all. Now we're going to have to draw a hilariously out of scale one to make this nicer to follow. Okay, so here's my slope, right? Here's my massive person on it. Okay, this skier is getting pulled by a force which is, what was it, 300? Yeah, 300 newtons horizontal. So this is parallel with this, and our angle here is 20. Don't think I meant to do two examples both at an angle of 20. Okay, now what do we have to find? The components of this force which are parallel and perpendicular to. So our parallel component is going to be here, and our perpendicular component here. Now, the thing that's awkward about this is the angles. The reason I wanted to draw such a big person here was I think it makes it easier to see what angles are going on. See the way this is parallel to this and this is parallel to this? It means we've got a wee corresponding arrow or angle situation going on here. So this angle here is also going to be 20, right? Now, let's see, look, that's C and D instead of A and B. Well, so C, parallel to, is going to be the original force 300. To get to the parallel one, we go across the angle, so cos 20, and that gets 281.9. And then the perpendicular one is our original force sine, because we don't go across the angle, 20, and that gets 102.6. Oops. Okay, so that is the notes and the examples on that. What I need you to do now is the questions on, let me see, 103 and 104. Okay, and then send me in pictures of those being done, or those done. All right, see you next day. Bye.